Okay, now the optimum design for a steam system will largely depend on whether the steam consumption rate has been accurately established. This will enable pipe sizes to be calculated, while pipe components such as control valves and steam traps can be sized to give the best possible results. The steam demand of the plant can be determined using a number of different methods. First, we list them, then we will discuss each one of them in detail. These are calculation, measurement, and thermal rating. In the calculation method, by analyzing the heat output on an item of plant using heat transfer equations, it may be possible to obtain an estimate for the steam consumption. Although heat transfer is not an exact science, and there may be many unknown variables, it is possible to utilize previous experimental data from similar applications. The results acquired using this method are usually accurate enough for most purposes. Examples will be discussed in later videos. Here, steam consumption may be determined by direct measurement using flow metering equipment. This will provide relatively accurate data on the steam consumption for an existing plant. However, for a plant which is still at the design stage or is not up and running, this method is of little use. Lastly, the thermal rating, or simply design rating, is often displayed on the nameplate of an individual item of plant, as provided by the manufacturers. A typical example of this is now shown on screen. These ratings usually express the anticipated heat output in kilowatt, but the steam consumption is in kilogram per hour, and this will depend on the recommended steam pressure, as we will discuss further ahead. Keep in mind, though, a change in any parameter which may alter the anticipated heat output means that the thermal rating and the connected load, so the actual steam consumption, will not be the same. The manufacturer's rating is an indication of the ideal capacity of an item and does not necessarily equate to the connected load. In most cases, the heat in steam is required to do two things: to produce a change in temperature in the product, that is, providing a heating up component, or to maintain the product temperature as heat is lost by natural causes or by design, that is, providing a heat loss component. In any heating process, the heating up component will decrease as the product temperature rises and the differential temperature between the heating coil and the product reduces. However, the heat loss component will increase as the product temperature rises and more heat is lost to the environment from the vessel or piping system. The total heat demand at any time is the sum of these two components. The equation used to establish the amount of heat needed to raise the temperature of a substance can be developed to apply to a range of heat transfer processes, as depicted here, where Q is the quantity of energy, M is the mass of the substance, C sub P is the specific heat capacity of the substance, and delta T is the temperature rise of the substance. In its original form, this equation can be used to determine a total amount of heat energy over the whole process. However, in its current form, it does not take into account the rate of heat transfer. To establish the rates of heat transfer, the various types of heat exchange application can be divided into two broad categories. These are non-flow type applications, where the product being heated is a fixed mass and a single batch within the confines of a vessel, or flow type applications, where a heated fluid constantly flows over the heat transfer surface. Let's examine each category in detail in the next couple of videos. In non-flow type applications, the process fluid is held as a single batch within the confines of a vessel. A steam coil situated in the vessel or a steam jacket around the vessel may constitute the heating surface. Typical examples include hot water storage calorifiers, as shown now on screen, and oil storage tanks, where a large circular steel tank is filled with a viscous oil requiring heat before it can be pumped. In some non-flow type applications, the process heat-up time is unimportant and ignored. However, in others, like oil refinery tanks, it may not only be important, but crucial to the overall process. Consider two non-flow heating processes requiring the same amount of heat energy, but different lengths of time to heat up. The heat transfer rates would differ, while the amounts of total heat transferred would be the same. The mean rate of heat transfer for such applications can be obtained by the following equation, where m is the mass of the fluid, C sub P is the specific heat capacity of the fluid, delta T is the increase in fluid temperature, and T is the time for the heating process. To illustrate how this equation can be used, let's consider the following example and calculate the mean heat transfer rate. Here, a quantity of oil is heated from a temperature of 35 degrees Celsius to 120 degrees Celsius over a period of 10 minutes. The volume of the oil is 35 liters. Its density is 900 kg per cubic meter, or 0.9 kg per liter, and its specific heat capacity is 1.9 kilojoule per kilogram degree Celsius over that temperature range. So let's determine the rate of heat transfer required for this non-flow application. Using the density and volume, the mass of the oil can be calculated as follows. Now, we plug in our variables in the heat transfer equation, as seen here, for a result of 8.48 kilowatt. Now, it is important to note here that this equation can be applied whether the substance being heated is steam, a solid, a liquid, or a gas. However, it does not take into account the transfer of heat involved when there is a change of phase. The quantity of heat provided by the condensing of steam can be determined by this next equation. So, the quantity of heat equals the mass of steam times the specific enthalpy of evaporation of steam at the prevailing pressure. It therefore follows that the steam consumption can be determined from the heat transfer rate and vice versa as follows, where Q dot is the mean heat transfer rate, M dot is the mean steam consumption, and H sub Fg is the specific enthalpy of evaporation of steam at the prevailing temperature and pressure. Now, at this stage, if we assume that the heat transfer is 100% efficient, then the heat provided by the steam must be equal to the heat requirement of the fluid to be heated. This can then be used to construct a simple heat balance, in which the heat energy supplied and required are equated, as seen here. As a result, the following third equation is obtained. Okay, to illustrate how this new equation can be used, let's consider the following example. Here, a tank containing 400 kg of kerosene is to be heated from 10 degrees Celsius to 40 degrees Celsius in 20 minutes using 4 bar gauge steam. The fluid has a specific heat capacity of 2 kJ per kilogram degree Celsius over that temperature range. The specific enthalpy of evaporation of steam at the gauge pressure of 4 bar is as follows. So let's determine the steam flow rate needed for this application. First, we determine the left-hand term of the heat transfer equation, m times Cp times delta T over time. This term is the heat energy required by the application. We plug in our variables for a result of 20 kJ per second. Assuming the tank is well insulated and heat losses are negligible, then the heat energy required and the heat energy supplied by steam are equated. Thus, the right-hand term of the equation also equal 20 kJ per second. Therefore, the steam consumption rate is as follows.